Hello everyone. This is section 1.2. It's about speed and velocity. We're going to learn about the differences between speed and velocity, how to graph it, and how to solve problems related to speed and velocity. Average speed versus average velocity. The average speed is a total distance traveled divided by total time taken to travel that distance. So since the distance is a scalar quantity, speed is a scalar quantity. The formula is V average is equal to delta D, which is a distance over interval of time. Unit is meter per second. Remember, not kilometer per hour, meter per second. Average velocity of an object in motion is its total displacement or change in position divided by total time taken for that motion. Velocity describes change in position over time. So since the change in position or displacement is a vector quantity, velocity is a vector quantity. The formula is similar to that above. V average is equal change in position over interval of time. Unit is meter per second, but since that is a vector quantity, has to be associated with direction. Now take a look on the diagrams on the left. There's a car, same car, moving left and right. The speed in any direction, since that is a scalar quantity, is the same. It's at 25 meters per second. However, direction matters at velocity. So traditionally, right direction is positive and left is negative. So that's why velocity on a car that is driving on a right is plus 25 meters per second, and velocity of the car that is driving on a left is minus 25 meters per second. Another consideration that you need to know is that since the speed and velocity has to do with a distance and displacement, they are not the same. They are the same if that motion is in a straight line in one direction, same direction. However, since that for a distance every meter counts, so path taken by an object matters. So distance is always different. It's bigger or equal than displacement. Here are some practice using average speed. A baseball roll along a flat parking lot in a straight line at a constant speed of 3.8 meters per second. How far will a baseball roll in 15 seconds? So what is given? Average speed is given and it is in a standard unit. Time is given and it is in a standard unit. Distance is required. We can use a formula, solve for delta D for distance, plug numbers, and then answer is 57 meters. A paper airplane flies 3.7 meters in 1.8 seconds. What is the airplane average speed? Same thing. What is given? Make sure they are in a standard unit. They are. And what is required is an average speed. Make sure you use proper symbols to write what is given, what is required, because when you're using formula, then you are using those symbols in the formula. So V average is distance over time. It's a 3.7 meter over 1.8 second. The answer is 2.06 meters per second. A cheetah can run at a maximum speed of 30 kilometers per hour. How far can the cheetah run at 3.27 seconds? So what is given? It's given a V average 30 kilometers per hour. However, that is not a standard unit. In order to convert it in a standard unit, you have to divide it with 3.6 kilometers per hour over meter per second, which is 8.33 meters per second. Time is given and it is in a standard unit. Distance is required. So we can use the same thing, use a formula, solve for distance, and then you have a standard unit of distance 27.2 meter. So again, it's very important to use standard unit because the answer has to be in a standard unit as well. I already mentioned where this number 3.6 came from. It is about kilometer. It is a 1,000 meter, and 1 hour is 3,600 seconds. So it's a 1,000 over 3,600. That means it's 1 over 3.6. So that's why you use dividing by 3.6 to convert kilometers per hour into a meter per second. Let's do some practice with the average velocity. If you see a sprinter goes from 0 to 50 meter running, and then from 50 meter goes back to a 0 walking. The first sprint section or run section is 8 seconds. And the other one, return or walking section, is 40 seconds. So total is 48 seconds. So what it's looking for is the average velocity for first section, run, and then second section, which is walk, and then entire trip. We can just mark the positive direction. It is on the right, and you take a look on the arrow there. So the arrow here shows you the positive direction of the x-axis. Okay, so let's start with the run section. Again, it's a displacement over time. The displacement is a change in position. So how the position changed? From final position minus initial. Final is 50 meter, initial is at 0 meter, over final minus initial time. So it started at the 0 second, obviously, and it took 8 seconds to go to a 50 meter sign. So it's a 50 minus 0, 8 minus 0, that is plus 6.25 meter per second. On a return section, you go from a 50 to 0. So 0 is a final. So 0 minus 50 divided by, and it takes 40 seconds. So total is 48 seconds minus 8 is 40. And the answer is minus 1.25 meter per second. And makes sense. So if you see the arrow on a walk, under the walk, it is opposite direction of the positive direction, which is, that is -1, and is expected to be negative. For an entire trip, you started at 0, you ended up at 0, so that means 0 minus 0 is 0, divided by the entire trip was 48 seconds, lasted 48 seconds. So 48 minus 0 is 48, but 0 divided by any number is going to be 0 anyways. So the average velocity is 0 because change in position or displacement is 0. So that is a learning opportunity here, that yes, although you are moving, average velocity can be 0, which in a normal way of thinking, you cannot think that speed can be 0, but velocity can. Some more practice with the average velocity. On a windy day, a position of the balloon changes as it blows 82 meters north away from a child in 15 seconds. What is the average velocity of the balloon? Again, what is given, what is required? Make sure that all of them are in a standard unit, and then write the formula and plug the numbers. So it's 82 meters north divided by 15 seconds. It is a 5.5 meter per second north. So obviously the direction of that velocity comes from direction of change in position or displacement. Next one is a subway train travels at the average velocity of 22.3 kilometers per hour west. How long will it take for the subway train to undergo a displacement of 241 meters? What is given, what is required? Just write it there on the top left corner. Displacement is 241 meter west. Average velocity is 22.3 kilometers per hour west, and time is required. Thing is, we have a problem here. Average velocity is not in a standard unit, so that's why you can change it to meter per second. So 1 kilometer is a 1,000 meter, and 1 hour is a 3,600 second. So it is pretty much ended up to a divide 22.3 with 3.6. So that's why that 3.6 came from. And the answer is 6.19 meter per second west. Now we are ready to solve for time. Time is delta D over V average. You can plug numbers now. You're ready. All are in a standard unit. So if you see that the west and west cancel, the direction cancel because the time is a scalar quantity, and you have 38.9 seconds. When we compare average speed and average velocity, we have to take into consideration what they are equal to. So they depend on, average speed depends on a distance, and average velocity depends on a change in position or displacement. So the magnitude of average velocity of an object is always equal or less than average speed. So when they are equal, when it's a straight line in one direction. So let's compare that section that we did already before from a 0 to a 50. For a sprint section, the average velocity was plus 6.25, but since that we are talking about magnitude only without considering sign at all, so now we can say magnitude of average velocity is 6.25 and average speed is 6.25. Now for the second section, remember that the average velocity for a walk section was minus 1.25, but now we are talking about magnitude only. So the magnitude of average velocity for a walk section is 1.25, so is average speed. However, so that means that the magnitude of velocity is equal to average speed. So when we compare now in a round trip, so when is the direction does change for the entire trip, things are different. And that's what you see, that average velocity for an entire trip, which we did already calculated before, is 0 divided by 48 because of the magnitude of displacement is 0. So that means that magnitude of average velocity is 0. But average speed is not, because in an average speed, distance is considered, and a distance, every meter counts, no matter what direction. So we have a 50 meter in a positive direction and a 50 meter on a negative direction, although in a displacement is 0, in a distance is just simple addition of 50 plus 50, 100 meter. So the average velocity is 0, but average speed is 2.08 meter per second. And obviously 0 is less than 2.08, so we came to a conclusion that we had that before, that average velocity, magnitude of average velocity is equal or less, and that is example for less than average speed. Now we are going to talk about position time graph. So graph and slope we learned already in grade 9, so the prior knowledge would be very useful here. However, you can start learning anytime. A position time graph is a graph that describes the motion of the object with a position on a vertical axis, traditionally was y-axis in a grade 9 math, and a time on a horizontal axis, which is x-axis on a xy coordinate system. For now, in physics, we use position time graph. The slope of the position time graph gives the velocity of the object. So slope is a rise over run. So what do? We do a change in a y-axis, which now is a change in position, over change in an x-axis, which now is a change in time or interval of time. So basically it's a change in position over time. That is slope, and that is average velocity. We should be able to interpret the motion just by looking at the graph. So here is a one-dimensional graph, which is telling us that at a time 0, when it starts, the object was at 1 meter from a reference point, and it moves at a positive direction to a 3 meter on another second, and then from 3 to 4 in a time 2 second, and on a time 3 second went back to a 2 meter from a reference point, and then on a 4th second time it went to a minus 1 meter. That means in opposite side of the reference point, 1 meter from a reference point, but in opposite side. So yes, we can understand that, but the best way to actually draw a graph is what we already are used to. We're used to this space and time graph. It's a very clear in this graph that yes, when time was 0, the position was at a +1. At a time 1, it was a +3. Time 2, it was a +4. Then on a time 3 second, went back toward the reference point, and then somewhere 3.6 or 3.7 crosses the reference point, and on a 4 second time, it went to an opposite side of the reference point at 1 meter away from reference point, but on a negative side. So now we have a space-time and we can analyze it. We can use this graph to calculate average speed. So yes, it is useful, the graph on the left is useful to count what distance that object traveled. For example, from time 0 to 1, it travels 2 meters. So from 1 to 2 to 3. And then from 1 second to 2 seconds, it travels another meter, which makes 3. And another second, it travels 2 meters, which is from 4 to 3 to 2. And then from 3 seconds to 4 seconds, it travels 3 meters. So 2, 1, 0, -1. So it's 8 meters per 4 seconds. We know average speed is 2 meters per second. Now for average velocity, it is much easier with the graph on the right, because the average velocity is about where did you start and where did you end up. So you started at the +1 and you ended up at a -1. So it is a final minus initial. So final is -1 minus initial, which is minus +1. So it's a -1 minus +1, which makes -2, divided by 4 is minus 0.5 meter per second. And that is a slope that can, if you join 1.1 and -1 on that graph with a line, that is the slope of that line, which is negative 0.5. Now, how can we build the graph? We learned about building a graph in grade 9. However, now we have a slightly different with a graph that we are used to with the X and Y. Now we have position time graph. When a motion involves constant velocity, the displacement is the same during equal time intervals. So that is the easier one, which results in a straight line. So it's a linear one. So when we build a position time graph, and we can derive velocity time graph from it, one thing that we have to take into consideration is the same motion. It's an object moving. It's about one object that is moving, and we analyze the same motion in two graphs, position time graph and velocity time graph. So here is a table of data. If you take a look, it's a time from 0 to 8 seconds. So when you build time, which is a horizontal line, horizontal axis, we have to label that from 0 to 8, not less, but not much more. You can label it up to 10 if you want, but not less than 8. When we draw and label vertical axis, which is a position axis, if you see the numbers there, it's a 0 to 144. You can label that axis with 0 to 144, or maybe a little bit more, 150, but not too much, not a big number, because you're not going to use that space of the graph, but definitely not less than 144, because we cannot plot a last point. So you have to be careful when you label it 0 to 8 or 0 to 10 if you want, and 0 to 144 or 150. That would be reasonable, actually, labeling on y-axis. Make sure the x-axis, or a time axis in this case, and a vertical axis or position axis have nothing to do with each other. So if you see the scale was 0 to 2, 2 to 4 are equally, but has nothing to do with a 0 to 50 or 50 to 100 or 100 to 150. So they are totally independent scale for each axis. Now, what we do, we plot values. You see that you have 0 and 0 here, and we can put 0. And then we have 2 and 36. At a 2, we have 36. And at a 4, we have 72. And a 6, you have 108, etc., etc. So we draw a line that joins those points, and you take a look of the line itself. The steeper the line, the greater the slope, the greater the object displacement for a given time, which means the faster velocity, the higher velocity. So steepness of that graph is related to average velocity. So then we can use that line to calculate the slope of that line in order to build a velocity time graph. So slope of that line, which is a constant, represent velocity of the time. And you know already about how to calculate the slope and how to describe that graph. So that's how you build a velocity time graph. Again, one thing that I'm going to emphasize it again. Take a look of the time axis for position time graph, and take a look of the time axis on a velocity time graph. They match exactly. They have to be the same because it is the same object moving. Now you're describing it with a position time graph or velocity time graph, but time is the same. Another thing that I have seen people actually making mistake over time is that in a position time graph, you see a line that goes from 0 to a certain value. That is a straight line, and slope of the straight line is a constant. And when you calculate a constant, that has to be horizontal, not starting from 0. It has to be horizontal because that slope is equally everywhere that you can measure. If you pick 2 points from 0 to 2 or from 2 to 4 or from 2 to 8, slope has to give the same number because the slope of the straight line is the same. There are 2 types of motions, uniform and non-uniform motion. Motion with a uniform or a constant velocity is a motion at a constant speed, so magnitude, and in a straight line, so the same direction. So there are 2 components of velocity, magnitude and a direction. So both of them has to be the same, has to be constant. Motion with non-uniform velocity is a motion that is not at a constant speed and not in a straight line. So that means if the magnitude, direction, or both are changing, then the motion is non-uniform motion. Let me give you an example. If you drive in a highway, for example, and you put the car in a cruise control, and the highway is not always straight, it turns the curve. Now the speed is constant, so the magnitude is constant. However, direction changes. So that means that you are not traveling at a uniform motion, but you are accelerating. Now in a chapter 3, in a unit 2, we're going to learn how that is felt. How do you know that is accelerated motion? You're going to feel the inertia. You're going to feel your body is going to lean to the direction that we're supposed to be at the beginning before you turn. So that's how you feel inertia. That's how you know that you are accelerating. More about this you're going to learn in the future, but just to give you a heads up that non-uniform motion has to be with a magnitude, direction, and or both. One of those or both are changing, then there's no constant anymore. Is a non-uniform motion, which is accelerated motion. So we are going to study only motion with a uniform acceleration, or as we call it, uniformly accelerated motion, when an acceleration is constant. When acceleration is not constant, it's so difficult to use any formula, or you can use graph to analyze it, but it is very difficult to analyze that non-uniform accelerated motion, which is very complex. Keep it simple. We are talking about uniform motion and uniformly accelerated motion. By looking at the position time graph, we can determine what type of motion the object is undergoing. We can compare and contrast the following position time graph. For example, if you take a look at the graph A, the graph A position doesn't change regardless of the time. That means that object is stationary at a position that is east of the reference point. In graph B, again, the position does not change. However, if you take a look, it is the opposite of east, which is west. We can say that object is stationary, is located at west of the reference point. Graph C, position changes and is moving toward east. And graph D, position changes and is moving toward east. That's the same, isn't it? But the graph, they are not the same. So what is the difference between graph C and graph D? So graph C is moving at a slower rate than graph D because graph D is steeper. So the steeper the graph, the bigger the slope, the bigger the average velocity. Now, what about graph E? If you see a graph E, it is moving at the negative direction. So by time is approaching toward reference point. So that means velocity is negative. So in a graph E, the object is moving at a certain speed that could be comparable with the graph D. However, in a contrast with graph D, which the object is moving away from reference point toward east, graph E, the object starts from east but is moving toward reference point in a west direction. Build a velocity time from a position time graph. Here's a practice, and there is a position time graph given. It's very clear that there are 3 segments on that graph, from 0 to 3, from 3 to 5, and from 5 to 6. And what we do, we calculate the slope of the position time line or segment, and we can build a velocity time graph right below. Remember, the time has to be the same, has to match, because it is the same motion described in 2 different graphs. So then we have a segment, the first segment, we get 2 points there, and we calculate the slope. The slope for 1 to 3 is, again, rise over run, or change in position over change in interval of time. So interval of time is 3 minus 0, and position is 15 minus 0. So as I said, you have to write a 0, although that doesn't change anything on calculation, because slope is about change. So change in a position over change in interval of time. So slope is a 5 meters per second. It's a positive. The second interval is from 3 to 5. Then we do the same thing, although as you practice, sometime you will realize right away that that slope is 0. So slope of the horizontal line is 0 because nothing changing on a y-axis. So 15 minus 15 is 0, and if you divide 0 with any number, that will give you 0 anyways. And the third one, from 5 to 6, you do the same thing. Change in position divided by interval of time. So final one is 0 and initial is 15, so 0 minus 15 divided by 6 minus 5, that will give you minus 15 meters per second. Then what do we draw? We draw a velocity time graph. We have to make sure that time has to match with that above graph, has to match. Then you can take into consideration that positive value are up to 5, but the negative value is up to negative 15. So when you draw x-axis or a time axis, you have to take into consideration the space. And it's very clear there. I left 1 quadrant for top and 3 on the bottom. Then interval is 0 to 3, correct? It's a constant slope from 0 to 3. So the constant value is graphed with a horizontal line for that segment from 0 to 3. Now, segment number 2 is 0. So that means from 3 to 5, has to be 0. Horizontal, 0. And then segment number 3 from 5 to 6 is minus 15 and has to be underneath at minus 15. And that is the graph. And here is a challenge of the day. It is calculating average speed and average velocity. Let's start with a problem. A car travels uphill at a constant speed of 35 kilometers per hour and return downhill at a constant speed of 65 kilometers per hour. What is average speed of the round trip? I have to warn you that answer is not 50 kilometers per hour. It is less. And the next one is, what is the average velocity of the round trip? B is not really challenging because that is easy, but I want to challenge you by calculating the average speed of the round trip. So uphill and downhill, and you don't really know the distance. So you're going to figure out that distance you don't really need. See you next time.